Dr. J. Carus, our fifth speaker of this series, came to the United States while a child from Vienna, Austria, and grew up in the Chicago suburbs. He completed his undergraduate and graduate work at the University of Chicago. Incidentally, his graduate work was completed under the guidance of Dr. Paul Weiss, who spoke at this series 2 years ago. Dr. Carus has pursued at least 3 careers and has done so most successfully in the opinions of his colleagues. His research and numerous publications have focused on the development of the amphibian nervous system and on metamorphosis. I hope that we shall hear some of this work today. Secondly, his administrative career includes being the chairman of the Department of Zoology at the University of Iowa for 10 years. Thirdly, Dr. Carus' work as a teacher has been truly outstanding and memorable. I know, for he was my teacher and major professor for the doctorate. His excellence as a teacher and his concern for his many students have made this career especially meaningful for us, his students, although perhaps rather selfishly. Dr. Carus just completed a term on the Cell Biology Study section of the National Institutes of Health and continues as a consultant to a facilities panel for the National Science Foundation. He is a member of the Society for the Study of Development and Growth, has been treasurer of the American Society of Zoologists, and is now on the American Institute of Biological Sciences Governing Board as the representative from the American Association of Anatomists. He is also a member of the International Institute of Embryology. It is with great pleasure that I present to you Dr. Carus.
Thank you, Dr. Sprague and Dr. Reynolds. It's indeed very pleasant to be here, to have a chance to visit again with Dr. Reynolds, and to have an opportunity to address an audience in a facility of this very pleasant and very impressive sort, and not to speak of having the opportunity to follow my own mentor, Dr. Weiss, over an interval of just a few years. It's always very nice to hear gracious words about oneself. I see that there are many young women in the audience, and perhaps this would be one of the times to indicate that Dr. Reynolds was, I believe, the 5th young woman who worked with me to receive her doctor's degree, and all of them are now continuing in careers in biology. The title of my talk today implies that hormones are present as coordinating mechanisms in certain organisms. In fact, hormones are present as coordinating mechanisms in a very large fraction of the organisms with which we deal, with which we are familiar. I need only point out that in arthropods, those insects, crayfish, and their relatives, that the problems of molting, that is, the actual fact of molting, is controlled by hormones. And if you think of the billions of insects which you might see or encounter under particular circumstances and which you certainly know exist, and realize that in each of these mechanisms are active in converting them from one phase to another in their larval period as they molt, as they go through pupation, and as they emerge from the pupa in the adult, I'm sure you'll recognize how very important hormones are as coordinators in development. Now, we shouldn't ignore vertebrates, and we tend, of course, to be concerned with ourselves, with human beings. And all of us have experienced the awakening of certain hormone activities at a particular time in life as we come to sexual maturity. These particular features are, of course, also under hormonal control. Now, we can also observe this in other vertebrates, some of them who are seasonal breeders, such as the deer. And there is no question about the relatively docile behavior of the male deer during much of the season, and then his serious aggressiveness under certain circumstances during the rutting period. And if we watch barnyard fowl, we're aware of the differences in their behavior there. And we should also be aware that this behavior can be changed by injecting either the male or the female with male sex hormone, changing their position in the social hierarchy of the barnyard. Now, it would obviously be impossible to do more than give an extremely brief and superficial survey of hormones as coordinating features in development unless one were to pick a particular area with which to deal. And this is what I've chosen to do, and particularly in the area most familiar to me. I'm sure all of you have seen tadpoles. And you know that tadpoles metamorphose or transform into frogs, and then at some future time the frogs get together and lay eggs, and the eggs hatch into more tadpoles, and so it goes in the ponds and ditches of this area and virtually every place else in the United States and most other parts of the world. How do tadpoles know when to metamorphose? How do they bring about the coordination of events which permits them to live an aquatic life while living an aquatic life to become adapted to a life on land, and then actually transform into this situation where they live at least on the fringes of the land, out of water? And how do they do this in such a coordinated way that each of the systems involved changes in coordination with all of the others? That is, the tail doesn't disappear as a swimming organ until all four legs are present and all four of them can be used. The animal does not emerge on land until it has the external type of ear for perceiving airborne sounds. It does have a lung very early in its existence, but it doesn't have all of the mechanisms for complete lung breathing, for effective lung breathing on land, until sometime later in the larval period. When it's on land, it has the job of keeping its eyeball wet, just as we have. We, of course, wink in order to do this. The tadpole can't. It doesn't have any eyelids. But as it prepares to metamorphose, it gets the eyelids as a result of certain hormonal actions upon those cells which are destined or predestined to form the eyelid. I simply listed these particular items as features, individual features, which the tadpole somehow has built into its genetic information system, controlled by hormones, leading ultimately to its transformation. Each of these events so keyed to the others that the tadpole is at all times capable of existing either on water or as it transforms on land, never at any time being inviolable so far as its environment is concerned. Now, what I should like first of all to do in terms of the slides is show you that we have certain features which we can see in tadpoles which will permit us to divide up the larval period into a series of stages. So thereafter, we can refer to a particular level of development by a numerical stage. And this particular staging series was conceived by Dr. Cecil Taylor and myself about 25 years ago, published in 1946. It divides the larval period into 25 particular stages. And what I want first of all to do is show you that we have, in fact, criteria to divide the tadpole in this way. And so the first slide will give us an overview of what happens in development, starting when the tadpole is 10 millimeters long and begins to feed. Up to the length of 10 millimeters, we have an embryo which depends upon the yolk present in the original egg to get it to that stage. This is for the ordinary leopard frog, which is common in this area. And if we measure the length of this animal, we find that it gets to be about 3 inches long, or 75 millimeters, before the tail begins to shrink. And you can see that there is first a relatively rapid rate of growth, then a slowing down of growth in terms of length, and then a very rapid shrinkage as the tail disappears, and we wind up with a froglet at stage 25, lacking its tail completely, adapted to life on land, and about 1 inch long. Now in this slide we see at the top the appearance of the mouth area of the tadpole as it's beginning to feed. It has horny beaks and these little tiny teeth around it. so it can rasp on soft vegetable foods. And then we have an indication of what the hind limb looks like. Now, the hind limb develops at the base of the tail, of course, and as you can see in the drawings at the bottom, the hind limb is first a bud, and then at stage 5 it develops a bend, and that bend is the first indication of the knee. When you were embryos, you had essentially the same kind of development of your limbs. Now we'll continue this particular sequence, and here we have stages 6 through 10, in which basically we follow further the appearance of the hind limb, and particularly of the foot, and you can see by the numbering, 1, 2, 3, 4, 5, the order in which the digits appear, number 1 being the equivalent of the big toe. And you can see that these appear in sequence, and that as they appear, the outline of the limb changes. And now we go to still later stages. We can see further developments of the limb, and the arrows at 15, 16, and 17 point to little bumps on the underside of the toes, which are little pads helping these animals to establish a frictional contact against the substrate and when they jump or walk, and they also develop in sequence. At stage 17, yes, I think you can see the arrow. At this area, between the hind legs, there is a expansion of the ventral tail fin, which is known as the coacal tailpiece, and its beginning resorption is the first indication externally that this tadpole is about to lose its tail. And in this next slide, we can see how this area shrinks, as shown at stage 18. Then at 19, where the arrow is indicated, there appears to be a hole. This is not really a hole. This is an area of the skin which has become thinned. It's being eroded away so that there are only 2 extremely thin layers, and it is inside a chamber behind that skin that the front legs have been developing coordinately with the hind legs. They just haven't been seen because they've been inside this chamber adjacent to the gills. And now at stage 19, the skin begins to erode. At stage 20, it actually ruptures so that the front legs can pop out. And the visualization of the front legs marks stage 20. And from then on, you can see the shortening of the tail, the broadening of the mouth with the gape of the mouth moving backward, and at X, the development of the external ear, the eardrum. And here we have now the completion of metamorphosis, the final shortening of the tail until it's no longer present as a nubbin, and you can see the ear below and behind the eye, as you can see the eardrum. Now, just to go through a few of the changes which mark the adult or metamorphosing animal as different from the tadpole. At the left, we have a drawing of the orbit containing the eye in the tadpole. That's 3A. And you can see the optic nerve, which is unnumbered, and then the various numbers refer to different extrinsic ocular muscles. On the right, one has a metamorphosed frog, and you can see how much heavier the muscles are, and you can see that the shape of the eyeball has changed. This is one of the things which is involved in metamorphosis. Another is pictured here. This happens to be upside down, but it's not particularly significant. Off at your right, you can see one very large nerve cell. In the tadpole, there are just 2 such cells, one on each side. And after metamorphosis, these cells disappear. Now, as we can see in the next slide, when we focus upon the nuclei of these cells, at the left, we see one of these cells prior to the time that a significant amount of hormone has been released in the tadpole, as we see the nucleus of such a cell. And at the right, we can see that it's larger. This is after the tadpole has been subjected to a certain amount of hormonal stimulation. And this cell appears to have the characteristic of growing when stimulated by the appropriate hormone, and then when the hormone stimulus is withdrawn, a shrinking. And here we have a review of this, perhaps 10 years ago, by one of the Italian workers, Stefanelli, showing the individual nerve cell, the appearance of the tadpole at the time the nerve cell looks like this, and then its shrinkage after metamorphosis, indicating, again, a particular metamorphic event, the last phases of which carry on well beyond metamorphosis. And now, to give you one other example, you can see the pale white lines starting above the eyes and moving on backward. They're broad and pale. This happens to be a tadpole that lacks a pituitary gland. It lacks it because we took it out. And then we have stimulated it in a particular way, and it permits us to visualize these broad white bands. These are bands of developing skin glands. The tadpole doesn't have these until this time, and then in the later phases of metamorphosis it develops them. And now very quickly I'd like to go through the development of these glands. In the middle at the top you can see an aggregation of about 5 cells, which marks the first indication of these glands. This is at about stage 13 in that series of 25 stages. At the bottom you can see perhaps 10 cells in a group. The gland has grown in the intervening time. If we go on to later stages in development, here we now have stages 15 and 16. You can see how these groups of cells have developed into hollow glands, and at the bottom right you can see that the gland is hollow and that it has a granular secretion in its middle. Now if we continue to still later stages, we can see how these glands grow, and as they grow they elevate the upper part of the skin, separating it from the lower part, until there is a stratum of loose connective tissue and loose cells between the two skin layers. And ultimately we get glands of this sort. The ones at the left are the granular glands, and the one at the right is a clear one or mucus gland. And you can see how much bigger these are than the original groups of gland nests. All of this is under hormonal control. Now, in order to summarize this, we have an indication of when the gland nests appear, how long gland nests continue to appear in terms of the staging symbols at the top, and dealing with the granular or serous glands at the top and the mucus glands at the bottom, we can see that these two sets of glands are somewhat out of phase with respect to their development. For even though we're dealing with the skin and with two sets of glands growing side by side, the rate at which one gland grows or develops is different from the rate at which the other kind of gland immediately adjacent to it develops. And here we have an indication of one of the features which is very important in the appropriate timing of a hormonally controlled sequence of events, namely that one kind of tissue, even though it's only a little different from another, may have quite different kinds of capacities to respond to the same stimulus, in this case, an identical hormone. And here is a cross-section through the base of the tail of a tadpole. You know it loses its tail, but there isn't a hollow spot where the tail left. That area is capped over by skin from the tail base, which flaps down as the final little stub of the tail disappears. And if you look at the top of this section, you can see that there is fairly thick skin with glands present. And then as you look off toward the side, you can see where that thick area of skin stops, where that thick wavy line under the cells on the superficial surface of the skin becomes a thin wavy line, and that is the junction between the skin above, which is going to remain as the closure of the tail base, and the skin below, which has only tail-forming capacities and which is going to disappear, which will be resorbed in metamorphosis. We have here a cell-sharp boundary dividing those cells which are destined to survive and remain on the adult and those cells which are of utility only in the larva. Now, we can bring about the change which makes some of them survive and some of them die by adding hormone to the water in which these tadpoles swim, or simply letting them mature at their own rate. We cannot, at the present time at least, shift which ones of those cells will survive during the transformation and which ones will die. That is something intrinsic to those cells in that particular position, and whether they're going to be one type or the other depends upon their position and their very slightly different history in the preceding periods of their development. Now here you can see a cross-section through the midbrain of a tadpole, and you can see that there are mainly two different cell types, some very, very large cells, which regrettably have the name of mesencephalic fifth nucleus cells. We'll just call them fifth nucleus cells. These cells have processes which go to the jaw muscles, and in human beings and most other vertebrates with teeth, they also go to the tooth sockets. So if you should at some time be eating hash and suddenly find that there is a piece of gristle or bone in the hash and clamp down on this with your teeth, you will get an impression of pressure in your tooth socket as a result of these particular cells being receptive to that kind of stimulus. Now the frogs have them too. Now if we look at the next slide, we see that these cells have a developmental history. If we convert these figures to Roman numerals 1 to 25, we deal here with the larval stages of the tadpole. These cells first appear at the time the tadpole begins to feed. And up above we have the cell size represented as if it were a circle, but you must recall the cell is three-dimensional, and this should therefore be a sphere. And down below we have the representation of the nucleus of those cells. And you can see that between stage 1 and 12, there's virtually no growth. By stage 16, there is some. At 20 and 24, very nearly the end of metamorphosis, there is still more. And then between the end of metamorphosis and the adult condition, there is still more, both for the nucleus and the cell body. The cell body growing faster than the nucleus, so that the ratio of nucleus size to cell body size changes. Now we will relate these changes a little later to hormonal conditions. And here we are going to do so. One of our concerns is how can we in fact demonstrate that any particular kind of hormone is responsible for a given metamorphic event. Now, in terms of what has been done by others and what has been done very well indeed, we know that the pituitary gland, which lies at the base of the skull, produces a hormone of its own which has the capacity of stimulating the thyroid gland. And the thyroid gland then releases thyroxine and probably other kinds of iodine-containing hormonal entities, and these circulate in the blood of the frog, of the tadpole in this case, and are distributed all over the body. In some of the places they get to, they may be in contact with tissues which are incapable of responding, or possibly the concentration of the hormone at a given instant may be too low to bring about a given response. Or they may be in the vicinity of a cell or of a tissue which is capable of responding. Now, one of the questions we wish to ask in the control of metamorphosis was this one. Is the hormone, thyroid hormone itself, directly responsible for a given metamorphic event, or is there a chain of events whereby the thyroid hormone stimulates structure or organ A, and this in turn stimulates structure or organ B, and this in turn structure or organ C? And we thought the easiest way to do this was to compound tiny pellets which contained a large quantity of thyroxine, one of the thyroid hormones, and place such a pellet in various positions in the tadpole body. If the tissues were directly responsive to the thyroxine, then those tissues closest to the pellet should respond more vigorously, earlier, more actively than those tissues farther away. And one of our tests was the one which is diagrammed here. We have the midbrain of the frog on one side represented, and the space within this brain labeled the optic ventricle. In front of the midbrain, we have this oblong body labeled implant. This is a pellet made up of thyroxine and something in which it can be carried along. And the question is, will those cells, which are indicated here by the dots, these mesencephalic fifth nucleus cells, respond better or more quickly on the right side of the animal containing the implant than they will on the left side? If they do, we then have rather conclusive evidence that these cells respond directly to the hormone rather than indirectly by way of an intermediary system. And the next slide will show the results which we obtained. No, this one regrettably doesn't show that. It shows instead an actual pellet in place. And you will notice that on the right side, where the pellet lies, in the skull cavity, where the cartilage is really still very thin, you can see the wound area through which it was introduced, which is rather dark in the skin, and you can see glands developing to either side. Whereas on the left side, you see only one gland, and mainly gland nests. Now here we have an indication of differential response of the skin as a result of being close to or farther away from the pellet. Now the next slide will tell us something about the fifth nucleus cells. And here we have an indication of when we sacrifice particular animals after the pellet had been in place 5 days or 6 or 7 or 10 or 20. And we have cell size indicated on the vertical scale, and each bar represents a range of cells, 75 cells counted and measured on each side, and the range of their size is indicated by the height of the bar. The average value is indicated by the little line on the bar, and you can see that in almost every instance, the bar on the right is higher than the bar on the left. Not quite in every one, but in almost every one. You will also notice that the range is such that in almost every instance, on the right, there are bigger cells than there are on the left. Now, when this data were submitted to statistical analysis, we got the confirming information which we sought. In fact, the cells on the right side are larger than the cells on the left in a statistically meaningful way. And thus we can presume that these cells directly respond in their growth to the presence of this thyroid hormone, thyroxine. This then is one of the evidences which we needed to demonstrate this immediate and direct response. The next slide will show another kind of situation in which pellets were used. This is a cross-section through the fore end of one tadpole showing two sides. This is a very early stage of development of the limb. That little bulge sticking out is the forelimb. It has no bones internally. It really has no cartilage even. It obviously has no toes. But if you recall, we stated the forelimbs were present under the skin of the front of the tadpole adjacent to the gill. And you can see on the right side that there is a double layer of skin with some very wavy, thin, loose tissue in between those two layers. That is where the skin window will later develop. On the left side, the skin window has developed and perforated so that the limb is already exposed to the outside. What's the difference between these two? On the left side, a pellet was placed which contained thyroxine adjacent to where we expected the skin window to develop, and the skin window did develop there. On the right side, a pellet not containing the hormone thyroxine was placed adjacent to where the skin window should develop, and the skin window did not develop. So in the presence of thyroid hormone thyroxine, the skin window went ahead and did what it was supposed to do. It regressed. The cells there disappeared. Another example of direct action of thyroid hormone upon a responding tissue. I wonder if I might have the lights, and if you'll save that slide for a moment. Now, what are the other features that we have to be concerned with in order to demonstrate a coordinated mechanism for the control of metamorphosis? I implied earlier that if the tadpole were supplied with thyroid hormone in concentrations which might be too low, it would not respond, and it would remain as a tadpole. This particular hormone can be provided to the tadpole in the water. We can dissolve thyroxine, put it in the water in which the tadpoles are swimming, and see what happens. If we dissolve enough, it will proceed through various events of metamorphosis. On the basis of work mainly of others, particularly of Dr. Etkin of New York City, of CCNY and the Albert Einstein Medical School in this country and others elsewhere, it can be demonstrated that tadpoles on their own begin secreting thyroid hormone in extremely minute quantities very soon after they begin feeding. By stage 7 or 8, they're secreting significant quantities of hormone so that we can use bioassay methods to demonstrate this. And over the rest of the larval period, the concentration of thyroid hormone, which is secreted, released into the blood, rises slowly but continuously until about the stage when the forelimbs emerge, or perhaps a little later, and then there is apparently enough present in the blood to carry through the rest of metamorphosis, and there is a sudden slowing down of thyroid hormone secretion. So there is a gradual increase in hormone concentration, and there is a gradual acceleration in the rate of metamorphosis. Now, we can prevent completely this sequence of events by either removing the thyroid gland directly or by removing the pituitary gland, which in turn controls the secretion of the thyroid gland. Since the removal of the pituitary gland, or I should say its rudiment in the embryos, is a far simpler operation than the removal of the thyroid gland, we usually choose to remove the pituitary gland. And if we do so, tadpoles will develop and grow until their limbs are in about stage 7. And then they stop developing completely in terms of further change in limbs. They may grow so that the tadpole becomes longer and longer, but in terms of metamorphic events, changes leading toward those structures which will permit it to live on land, nothing further happens unless we provide thyroid hormone to it. Now, we can provide thyroid hormone directly by putting it in the water, or we can inject them with pituitary materials. We choose, for control reasons, to provide them with thyroid hormone. And now the question comes up, are there thresholds in particular events in metamorphosis? Are there minimal requirements for particular metamorphic events? And here is where Dr. Etkin and I differ, and I should like to indicate something about our difference and the kind of evidence I have to substantiate my point of view. I'd be delighted if you were here so we could discuss later our differences. He states that any concentration of hormone which will bring about any metamorphic event will, if permitted to act long enough, bring about all of the metamorphic events. The point of view I hold is different. It states that different tissues have different minimal requirements for particular metamorphic events. For example, when we deal just with the hind limbs, we know that a concentration of 2 parts of thyroxine in 1 trillion parts of water is the minimal concentration which will bring about some growth of the hind limbs. This concentration will, over a period of 4 or 5 months, permit these hind limbs in a hypothesectomized tadpole to go from stage 7 to stage 9, or maybe to stage 10. And then, no matter how much longer we keep the tadpole in this hormone concentration, providing the hormone fresh daily, it will not change further. However, any time that we increase the hormone concentration above this level, then the limb will respond again. And let us say we now change the hormone concentration from 2 parts per trillion to 20 parts per trillion. The limb will go to perhaps stage 12 or 15. And finally, if we get the concentration to about 500 parts per trillion, the tadpole will go clear through the metamorphic stages up to and beyond the perforation of the skin window and the release of the forelimbs so they can be visible. And for each concentration between those 2 figures, 2 parts per trillion and roughly 400 or 500 parts per trillion, the tadpole will come to a given stage, and if no more hormone is made available, it will stop at that intermediate phase of metamorphosis. And when I say stop, I imply that we have kept these tadpoles any place from 6 months to 12 months after the last change that we have seen, and then, for at least some of them, we have added more hormone to demonstrate that they're still sensitive to it and can continue. Now let me tell you one other aspect. This is a matter of threshold, and I will simply assert that for each of the tissues with which we have been concerned, we can demonstrate that there is a minimal concentration needed to achieve a given event, and that subsequent events will require higher concentrations. Now, about 10 or 12 years ago, my total facility in terms of space was one office about 10 by 17, non-air conditioned, and Iowa winters are, if anything, slightly colder than the winters here in Muncie. And in order to utilize as much space as possible, I kept some bowls of tadpoles on the window ledge. And on the window ledge in the dead of winter, the water gets pretty cold. And as I did my experiments, I had some space in the room where it was warm, some space on a table under the window ledge where it was cool, and some space on the window ledge where it was quite cold. And I observed the following. If the animals were kept on the window ledge at a given concentration, they didn't go nearly as fast, and ultimately they came to a stop at an earlier stage than did those animals kept at room temperature. And if they were taken from the window ledge and put onto the table in the room away from the window ledge, and hormone dosage was kept constant, they would again start metamorphosing and proceed for some little distance before they stopped once again at a much later stage. So here we had an implication that temperature was somehow involved, and it appears to be involved in changing the threshold values, that is, in increasing the requirement for thyroid hormone in order to bring about events in metamorphosis. And if you think about what happens in ponds over this country in winter where the bullfrog tadpoles are wintering, you will understand why it is that bullfrog tadpoles don't transform into frogs during winter. It's much too cold. The hormone concentrations demanded of them are much too high, and not until it warms up the next spring or summer will these concentrations be such that the thresholds are lowered sufficiently for the various tissues to change. So a second feature that we're concerned with here is timing as it's influenced by temperature. Temperature, apparently, changes the threshold, making the requirement for a given hormone concentration higher than before. Now, one other question remains, or two other questions. One of these is the readiness of tissues to respond. If we treat embryos before they started feeding with hormone, and then take them out of hormone, they will behave as if they'd never been stimulated. The embryonic tissues, up until just before the animal is ready to feed, are completely insensitive to the thyroid hormone. So the development of sensitivity is an embryonic phase. During the mid-larval period, all of the tissues which are going to respond are already ready to respond. We also know that the higher the concentration of a given hormone is, the faster will the responding tissues respond, so that as the pituitary increases its secretion, forces the thyroid gland in later stages of development to put out more hormone, the rate of metamorphosis accelerates. Now, the one other question I would like to raise here is whether these tissues, once they have begun to change, will continue to change on their own, or whether they will stop changing if thyroid hormone is withdrawn. And one of the best materials for this is the fifth nucleus cells, and the experiment which was devised for this is a very simple one. We took hypophysectomized tadpoles, which therefore on their own would not go beyond stage 7. We used 1/3 of these, 14 or 15 of them, as controls, and simply sacrificed them in the middle of the experiment. 28 others, and all of these were matched as groups of 3, the same size, the same stage, were placed into thyroid hormone solution, and half of them were sacrificed at the end of the experiment or the day afterwards. And the other half of this treated group was permitted to survive another 9 to 20 days, roughly, and then sacrificed. The question which we could ask, therefore, was this. We know that thyroid hormone brings about an increase in the size of the mesencephalic fifth nucleus cells. At the end of treatment, the cells in all of the experimental tadpoles should, on the average, be larger than the cells in the control tadpoles that were not stimulated. Will those cells which have grown remain large once thyroid hormone is withdrawn, or will they again shrink back to a larval condition? In the next slides, we'll detail this particular experiment. At the bottom, we have the controls, and we have measured nuclear size in cross-sections and cell size. And you can see the range indicated within the oblong and the average for these animals indicated by the vertical line. Series 1 represents those animals fixed immediately after the end of treatment, and Series 2 those animals fixed 9 to 20 days later when they had been without hormone stimulation for that interval of time. You can see that they have shrunk back toward the control side. Here we have an indication that these cells, though capable of responding and responding quickly, require the hormone in order to retain the more mature characteristics. We can also see that this is a different notion. Utilizing tadpoles which had been kept in weak concentrations of hormone until they had achieved the given stage indicated at the left, we were able to contrast hypophysectomized but stimulated animals with control animals. And the upper bar in each case represents the hypophysectomized stimulated animal, which is of exactly the same length and exactly the same stage as a control. And the length of the bar indicates the maximum size of mesencephalic cells. The length of the polka dot bar, the average size of the cells. The length of the crosshatched bar, the maximum size of the nuclei. And the length of the solid bar, the average size of the nuclei. And you can see that for each of these four particular pairs of animals, the stimulated animals have much smaller fixed nucleus cells than have the controls. This implies, first, that they have a higher concentration requirement in order to be stimulated than have the external features of the tadpole. The hormone concentrations we used here were far less than in the previous experiment. So even though we have cells which are sensitive to hormone, unless we exceed their threshold for response, we will not get a response. Now I'd like the projectionist, if you would, to skip to the very last group of slides and proceed with those. The very last group of slides. The one final item I want to deal with is the notion that thyroid hormone or thyroid hormones are not unitary. Biochemists who analyze the thyroid gland can find different kinds of chemical entities in it. Thyroxine, triiodothyronine, monoiodotyrosine, diiodotyrosine, and others. The question exists, do the tissues of the tadpole respond differently to different kinds of compounds? And we have obtained different compounds manufactured by chemists, exposed our tadpoles to them, and obtained some of the following grotesque results. And we must ultimately, in explaining metamorphosis, explain these grotesque results as well. Here we have a ventral view of a tadpole whose mouth is still larval, but that has these tremendous openings of the skin windows exposing the gills. This never happens in the normal tadpole. What we have done is stimulate the capacity to reduce the skin window to a much larger size than was ever normally experienced. Notice also the cloacal tailpiece is missing. Another slide will show the tadpole, which is still alive in the bottom of a pan of water and has almost all of its tail gone. The tail wasn't cut off, the tail resorbed. A normal tadpole metamorphosing, when its tail length becomes shorter than its outstretched hind legs, must have access to air. It no longer has adequate gill surfaces to breathe. This tadpole still has pretty good gills and is doing very happily underwater without much access to air. There is another showing a tail in a very much twisted and contorted position, never seen, to my knowledge, in normal animals, as well as the tremendous change around the gills. Here another one, remarkable. One never sees this in nature. We have here different hormone entities which show that they have different capacities to stimulate tissues than has thyroxine when applied in the dosages which we apply here. This animal looks particularly grotesque because it was not pictured until after it had been preserved. But before it was preserved, it was swimming around. It still has these external gills. The external gills were bright red. But you can see that its mouth is already widening, and the little air bubbles are simply trapped there during the process of photographing it. You can see how bulgy the eyes are because the eye muscles have developed. Just one more slide, I think. Yes, here we are. I just wanted you to see a picture taken from a frame of motion picture film so that you would get a notion that the gills of this creature, tadpoles, you know, never have external gills. Salamander larvae do, but not frog larvae. That this particular creature had beautiful bright red gills because the blood was still circulating through them. We have here a kind of animal never seen in nature, but produced here because we have used unusual hormones to induce its tissues to do something in a sequence which they were never designed to do. Now if I may have the lights. In closing, therefore, I would like to call to your attention that when we're dealing with control of development of metamorphosis, just one example of the many which could be used in the animal kingdom, we have to deal with a number of separate events. We must deal with whether the tissues are ready to respond. We must deal with whether the hormone is being supplied to these tissues, and if so, whether it's being supplied at a constant rate, at a decreasing rate, or at an increasing rate. We must be concerned with whether the tissues will respond at the same rate to minimal quantities of hormone or to much more than minimal quantities of hormone. In other words, do their rates increase when hormone concentrations exceed thresholds? We must be concerned with the influence of temperature, not only perhaps upon thresholds, but in nature, as to whether the temperature effect also acts back upon the thyroid gland and the pituitary gland. And finally, since we know that the thyroid gland is capable of producing different kinds of chemicals, several of which will stimulate metamorphosis, we have to know something about the product mix of the thyroid gland and at the rate at which these different entities are being released. Only when we have a reasonable understanding of each of these particular events will we be able to say with some confidence that we do, in fact, understand amphibian metamorphosis. Thank you very much.